Thank you everyone for joining us today. As Louise mentioned, this here is a project that's been long in the making. I remember first starting design on this back in 2016. It's been nearly 6 years now, and we're about to cross the finish line on it. So I really appreciate everyone making the time to kind of learn about its story, its narrative, because it is quite an interesting one. Because at the time when we first started, this was the city of Vancouver's first kind of dabblings into passive house. In fact, this was going to be their first non-residential passive house project. And what you'll learn today, and possibly maybe you've seen this previously in preceding presentations on this project, but Firehalls are not, simple buildings. They're actually quite complex archetypes. They mesh together this residential component, this commercial, office component, in between all this utilitarian and very industrial space. So there's a lot of process loads. There's a lot of energy that's being consumed in these fire halls, and so they're ripe for turning into high-performing buildings. And personally, I've worked on many of fire halls in my time, and it was through years and years of working on various different fire halls that we were able to kind of learn some great lessons learned that we tried to apply here. And so if you want to, like Louise mentioned, take a dive into into this project, particularly through the mechanical engineer's lens. Hopefully we can share some lessons learned, some challenges, some solutions, and I got some great pictures from site to be able to share as well. So like I mentioned before, this was the city's very first passive house project. It was also, the city of Vancouver also has a really robust green building policy. So all new buildings needed to be LEED gold. But it was very clear that as we started designing the building and through some of our previous experience, we knew that we'd be probably able to manage the loads to a point where we can even widen the scope of the sustainability objectives on this project to eventually incorporate the zero carbon, which at the time was a pilot program, and this was one of the first projects to apply for it. Primarily because for us in the Pacific Northwest, and particularly in Vancouver, electricity is fairly carbon free, not entirely carbon free, but fairly carbon free. So it was quite an easy step for us to widen that scope to include that. And then inherently, by taking such an aggressive measure through the envelope first approach of passive house to reduce energy, and then through some really interesting ways of designing systems to further reduce energy on the building, consider the possibilities of actually going net zero in energy. So this is a project with a few different accolades that it's hoping to achieve under its belt, but probably the one that takes the cake for the hardest was passive house. So before we dive right into the systems discussion, it's important to take a bit of a step back and really understand, fire halls and why they're such big energy pigs, right? The average here across all of City of Vancouver's portfolio shows that, the PER for these buildings is actually quite high. In fact, it's egregiously high. For buildings that are often, on average can range anywhere between 15 to about 20,000 square foot, right? And a significant portion of that hall space is actually dedicated to double height, apparatus-based storage, which isn't even tempered to a full 20 degrees. So it helps paint a bit of a picture for you to understand that, there's a lot of different process loads and energy being consumed in these halls. And so with our fire hall, the existing fire hall at the time in 1954, postmodern building that, was probably one of the worst offenders to kind of make the jump over into, the passive house realm, which was practically, an 80% cut. It's quite significant. And we knew that we had to do everything that we could from the envelope perspective, and HCMA, I think, did a fantastic job of addressing that, particularly considering as tight a site as we did have to work with. But we knew that the systems and the approaches for heat recovery and system selection were going to play a large role in tying the energy narrative in and finding solutions that were going to be quite fitting for this project. And so the system selection started with very simple conversations with the fire department and the owners. And for them, they had some very specific requirements, which were that they needed active cooling all throughout the year, particularly because of the fact that when firefighters return after a call, they're heat exhausted, they needed to be cooled, they needed the spaces to remain cool. And, you know, the average space temperatures of 20 to 25, you know, sometimes just wouldn't cut it. So they needed some spaces to be cooler than others. Noise mitigation was also another big thing for them. I'll share in the next slide a bit of a site shot for everyone to understand the context of that. But for those of you who do know this site quite well, it's off of Ninth Street, which is a very busy thoroughfare. There's like semi trucks rolling through there at all times of the day and night. So not only for noise mitigation was particularly key for the firefighters themselves to be able to get rest, but also just being conscious of the noise the building itself generated for the neighbors around the area, because there was, in fact, for the most part, residential RS1, so a lot of single family residential around the area. So they had to be very conscious of that. And like I mentioned, the city of Vancouver being, you know, probably one of the most, you know, I guess leading edge municipalities in the city within BC and really in North America, big emphasis on reducing carbon and really pushing the envelope, you know, pardon the pun, in finding ways of reducing their own footprint, and in doing so kind of tasked us with looking at low carbon solutions, which essentially right off the bat looked at, you know, natural gas free sources of heat, so looking at electric based systems. And so these big key requirements in the building essentially kind of pointed us down the path of electric-based, you know, heating and cooling systems, which inherently kind of lend themselves to heat pumps. And so, of course, you have, you know, the water to water, air to water, and air to refrigerant. And going through the pros and cons of each of these, we eventually settled on Geo-Exchange, and primarily for three key benefits in our that were kind of looked at across the board. And for the city and particularly the stakeholders, they understood the superior energy savings that can be realized through Geo-Exchange. You know, touching on the system resiliency aspect, you know, the big reason why you have greater levels of resiliency and energy savings is because you're sharing and exchanging heat and cooling with the ground, which is a lot more constant and a little less disturbed based on kind of your air to refrigerant or air to water systems, which rely on the outdoor air temperatures. But it has great noise mitigation opportunities because you no longer have these big outdoor units blowing at all times of the day and possibly causing a nuisance to the neighbors around them. But it also increases the service life of the equipment because everything's held indoors, nothing's being weathered over time. And so the maintenance people were particularly keen on that as well, because, you know, they didn't have to go up onto roofs to access any equipment. Everything was indoors in a nice, you know, thermally comfortable passive house for them to get access to. And a great thing about this project is, considering the Geo-Exchange field that's required for this project, you know, when you come to think about, you know, a passive house and really reducing the loads for this building for it's just about 19,000 square feet building, you know, really straddling the north and south lines of the property there, and with Ninth Street on the diagonal on the left, we had a very narrow site to work with to actually install Geo-Exchange. And so, you know, based on our modeling for the heating and cooling needs of this entire building throughout the year, all it took for us was just 12 boreholes. And that right there is a great story. You know, there's no backup heating in this building at all. There's no backup boilers, no backup, you know, cooling towers or anything. The Geo-Exchange field, in order to meet the 100% of the heating and cooling needs for this building, are just, you know, the small little portion of the site in the top left corner. Now, it being a very tight site as it was, we definitely talked to the city, and considering that we had a little bit more room to play with, we allowed for an additional 3 boreholes for a couple of reasons. The first one is just to mitigate some of the constructability risk with as tight a site as it was, to make sure that, you know, when we are digging, you know, about 300 feet down into the ground, if we hit a boulder, we have enough room to make up for an additional borehole here and there. And so that gave us the flexibility to do so. But it also gave us 30% more field space, which is actually kind of quite a big piece particularly on the climate resiliency standpoint, because, you know, as temperatures get warmer outside, and yes, the ground is somewhat shielded from that, but, you know, your building is still experiencing that extra cooling demand. And so as a result, having some additional storage in the ground to be able to mitigate that just increases the service life of the field, which actually, you know, allows for this building to, you know, have a service life much greater than, you know, what it was initially forecasted for. Most buildings are often designed for 50, maybe 80 years. This building was looking to essentially hit 100 years of service life. Now you're probably wondering, well, Scott, there's tons of room on the site. Why don't you, you know, put a whole bunch of, you know, boreholes across the site? Well, that's a very good question. Anyone want to take a guess how many boreholes you'll actually need to do this building if it was a code building? You know, try to take a guess in the chat. You know, let's see who guesses this right. I'll give you a few seconds to put your number in. You know, people, I'm not seeing the chat move at all. So maybe everyone's, oh, I'm seeing a few come in. Okay, excellent. The correct answer for those that are probably, you know, put something down is roughly 70 boreholes. And you'd effectively be covering your entire site with boreholes. So in addition to the green and the blue, the green and the red ones, you'd need the extra blue boreholes in order to make up the entire site, or to meet the heating and cooling loads 100% of the year with the building of its equivalent. Now, you know, the city was very clear with us. They didn't want boreholes to be drilled underneath the building itself or in lanes where the trucks could be running. So that really narrowed up our field. And you know, one thing I didn't share with you, which, you know, is worth highlighting, is that a portion of the site was actually actively being used for the training facility, which was put in place directly next to the Firehall, so that, the temporary shelter for the firefighters themselves to remain in operation while they were building it right next door to them. So you can see in that image that it's a tight squeeze on site, and you can see right there just the very southern edge of the building itself, straddling the property line. So we weren't kidding when we said this was a tight site. So all we had was just that little sliver on the left side of the site to be able to fit our boreholes when we looked at this entire project. And I'm happy to report that, you know, with some careful spec and conversations with Geo-Exchange contractors, that we were actually able to, you know, install each one of those boreholes in the exact locations that we had highlighted without any issues. Although, I mean, there was one issue, is actually the one at the very, you know, top left corner of the site, the one that's closest to that telephone pole, right at the corner of the edge of the site. And I think the only issue that they had was that they were a little worried that they were too close to that telephone pole, but it turned out that it was a bit of a non-issue anyway, and they were able to install it no problem. And the nice thing about this, you know, being such a discrete little site, is that each one of those boreholes are actually individually home run back to this one vault that's located in that bottom left corner there. That gives us the ability such that if any one of those boreholes is compromised, we could isolate that one borehole without impacting the rest of the field. Whereas larger fields, in order to help save cost, normally they're grouping all the pipes together. And so if one of those holes is compromised, you might see 4 or 5 of those go down, right? And so that gives us the ability of just really, you know, minimizing the downtime to the haul. It was a far more intuitive design that gave far greater resiliency to not just the firefighters, but the city of Vancouver from a maintenance standpoint and long-term operational standpoint. And really a great story to share, because, you know, the cost of doing the Geo-Exchange on this building actually was quite close to the cost of putting all the PV that went onto the roof. So a huge win for us there. Now I want to transition a little bit more into a more passive element of the building that was integrated into the overall system design and the impact that it had there, and that was the use of electrochromic glass on the building. And so I mentioned that, especially on the south end of the building, where we were straddling the south property line, fixed shading was a bit of an issue. And so we had to find ways of being able to mitigate, you know, particularly the harmful gains in the summertime with, you know, if I take a bit of a step back, you could see the amount of glazing that there was on that south facade. So we needed to be very conscious of that. And so electrochromic glass gave us the flexibility of being able to do that, but also just that flexibility in the shading options with its activation on and off between the winter and summer months. And that right there, you know, between its full activation on and off, you know, is quite substantial. It was able to just, you know, right off the top, shave about 14% of the load on the mechanical systems, which again, gave us an opportunity to be able to look at, you know, putting in, you know, lighter grade equipment, which is a little bit more readily available rather than commercial or institutional grade equipment, which comes in the bigger sizes. So it increased our ability to find different equipment to spec, which made it a little bit more cost effective in that regard. But altogether, you know, the costs there of just shaving wherever we could on the mechanical load allowed us to pay for some of these upgrades like electrochromic glass. And the neat thing that we did there, which at the time when we were in design was with View Glass, but ultimately Sage Glass was the successful proponent. You know, working with their teams, we know that, you know, this system could be integrated, like its controls algorithms were very simplistic in the sense that we can integrate them into the building control systems, because, you know, the way the system works is that, you know, it gets the sun shines on an irradiance sensor. Based on your exposure, it then says, all right, start tinting my glass, right? But, you know, we layered that into the building automation system such that we can look at harnessing the ability to turn on and off the shading based on our season. So depending on whether or not we're in the heating or cooling season, and in this case, if we're looking at the cooling season, we'd want to first look at activating the shading and waiting and actively allowing for the system to pause before activating any other type of system. And so if it's able to meet the space temperature or at least mitigate the gains such that our space temperature is satisfied, then we can sit back and relax. Otherwise, if it's not satisfied after a certain period of time, we can then look at boosting our HRVs if free cooling is an opportunity before actually activating you know, our active form of cooling to then deal with any potential loads. And same holds true in the heating season, except it's slightly reversed, depending on whether or not you are, in this case, kind of looking at, you know, deactivating the shading, and if it does help to mitigate the gains. Otherwise, you know, you look at activating your fan coil units and dealing with it more actively. It's transitioning to passive house. And more so on the ventilation side of things, you know, the one thing here that's worth sharing is that, you know, here is a bit of just a very high level overview to help give you an understanding of how many you know, heat recovery ventilators we had on the project, and B, how they were zoned. And what you'll come to realize is that, boy, there's a lot of HRVs on this project. What the heck were you thinking, Scott? You know, I mentioned at the time that this project has been in the making for quite some time. And at the time that we started, you'd be happy to know that Swagon was just about to enter our market. And the only other passive house certified component that was anywhere near this level of performance, or, you know, could offer some form of performance to us, were the Zender, you know, Comfo Air 350s, which really weren't tasked with being able to kind of operate at the amount of airflows that we needed to find in a Firehall. And so we were really lucky that, you know, Zender had brought in these units, and so we were able to design around that. But the one thing that wasn't in our advantage was that the react dampers weren't quite there. And so we zoned different spaces and occupancies based on their usage and occupancy patterns, so that the whole spaces or the whole zones could kind of ramp up and down based on, you know, peaks, the ebbs and flows of the occupancy throughout the space. And so, you know, the one benefit there too is that we also looked at decoupling our ventilation systems from our heating and cooling systems. So what that meant is that we ran separate ventilation ductwork than our heating and cooling equipment. So the heating and cooling equipment can recirculate and only operate when needed, whereas the ventilation systems operate all the time. And that gives us the opportunity to be able to significantly reduce the fan energy and a lot of that heating and cooling equipment, because it's not needed to run to supplement the ventilation load to those spaces. But, you know, like I said, why so many units? It was largely because at the time when we were designing, you know, we were in the midst of kind of working through that market transformation. And it's really great to see that in the past few years, you know, we've seen other HRVs come to market, like Flackwood. We've seen, you know, Multicross start to dabble in too. Oxygenate has units that are also available now. Same with Vantacity. So it's great to see a great slew and a wide variety of different manufacturers and manufacturers that have passive house certified components that can make, you know, bigger projects and more complex projects, or cater to those projects rather, a reality. Because otherwise, you know, it definitely becomes a bit of a challenge to be able to design bigger buildings with just Comfware 350s. And one piece of the ventilation puzzle that I definitely want to share is the topic of kitchen exhaust. And when you consider the fact that you've got, you know, 10 firefighters, 2 shifts, and 3 solid meals a day. In fact, that's one thing that you'll probably realize ever walking into a fire hall. It always smells absolutely amazing in there because there's always someone cooking, you know, and making enough food to feed, you know, the lot. And so you're looking at, you know, a lot of different meals, up to 60 meals a day. And so, you know, the one thing that we learned particularly on fire halls is that, you know, you'd be surprised how many kitchen fires actually get started in fire halls. When a call comes in and someone's working that kitchen, you know, they're going to be leaving right away. And sometimes they forget to hit the button to shut off all the equipment, right? And so you'd be surprised to hear how many times people go, answer a call, come back, and they come to their own hall and there's a fire started and they need to kind of deal with that own with their own mess. But the big story, or what I was leading to, is the fact that for them, they were really trying to, you know, make a case that they did not want to run exhaust to the outdoors. Or sorry, they did want to run exhaust to the outdoors. They were not big fans of recirculating air in the space because of the amount of smoke and their previous you know, experiences. And so they were quite adamant that this was something that, you know, could not shift, and as a or they couldn't shift their paradigm away from. And so, you know, working with the team and knowing this information quite early, you know, we looked at the variant designs to be able to look at the impact that it had on the overall. And yes, though it had a significant impact on, you know, the heating demand, you know, the overall impact that it had on the overall primary energy was, you know, quite small in comparison. And so that was just one of those decisions that as a team, we decided to kind of design around. And so it just meant that, you know, we had to find other ways of making up for that energy penalty. And so we found ways of being able to kind of balance the load, particularly on the ventilation side, such that, you know, the HRV that serves that zone can remain a little unbalanced just during those times of extended cooking. Which, you know, actually is a bit of a positive effect, because oftentimes when they're cooking over long periods of time and they're generating a lot of heat and steam in that space, if they're able to run the HRV at a bit of an imbalance and bring in a little bit cooler air, it actually provides the firefighters with a bit of relief, because they actually prefer to have the space a bit cooler anyway during cooking. So that was, you know, one way that we were able to address that. And of course, you know, with the penetration to the outdoors, thermal bridge free design, and finding ways to mitigate those as much as possible. Well, you know, you'd be happy to know that there's, you know, tons of products that are available on the market to be able to address that. So that was one way we were able to look at, you know, finding ways to reduce that load as much as possible. And lastly, I'd like to touch on domestic hot water, because I think that's always, you know, when we start reducing the envelope loads, the ventilation loads, you know, the heating, cooling loads as much as possible, domestic hot water becomes the next kind of elephant in the room that we need to address. And similarly, when we look at, you know, the approach that we apply from, you know, the passive house approach, this envelope first approach, it's really finding, you know, passive ways of reducing our load first before actively throwing technology at the solution. And so here, what we started with was really just utilizing drain water heat recovery wherever we could. And so, you know, very early in design, we tried to locate the showers, you know, in a location where it could facilitate the drain water to be collected in one location, so that we can then recover that waste heat and be able to then use it to kind of temper you know, the cold water that would then either, you know, feed up to the showers or over into a couple of tanks. And, you know, the first stage of active form of heating is through a couple of very residential commercial grade air source heat pump, you know, hybrid electric hot water tanks. And I'll touch on the dual benefit of these tanks because, you know, there was a bit of another design synergy there that that came from the use of these tanks. And then just to kind of touch on that, in addition to this, you know, these tanks, the nice thing about them, great to save energy, great for storage, but they're not really great for peak loads. And in this Firehall, you know, they're also responsible for a lot of gear washing. And so that's why a big reason for domestic hot water being so high in these buildings is not just the fact that you've got, you know, 10 firefighters that might need to take showers on a regular basis. But you also have, you know, a lot of gear washing that happens not just for this hall, but for other halls across Metro Vancouver. And so there's an extra hot water tank that's there in tandem, and that's just a direct electric tank. It's purely there for backup when, you know, they're dealing with those peak loads. And then that ultimately is the system and the methodology there that kind of serves the rest of the building. This is the one benefit that I do want to highlight here with these, you know, hybrid electric heat pump tanks. If anyone's ever seen these, they're quite, you know, quite neat, right? It's just a little heat pump that sits on your tank. It draws warm air from your space in, it blows cold air out. And as it kind of draws that warm air from the space in, it kind of transfers that heat in through via vapor compression cycle into the domestic hot water that's being generated, which then serves your building. Now you're thinking, well, you know, if this thing is just spewing a whole bunch of cold air, you know, finding opportunities to be able to utilize that is key. And for us, you know, particularly in a fire hall where you got IT and comms rooms, again, you know, through some of, you know, the work that we did with the HCMA very early in the project, co-locating these rooms where you've got, you know, cooling only process loads that are happening 24/7 allowed us to duct that cold air into these spaces and just allow for that hot air to just kind of transfer back in through that space and just kind of allow for this like passive cooling effect, if you have it. And, you know, what we were able to find is just, you know, doing some back of the hand calcs is that, you know, based on the amount of domestic hot water consumption they're forecasting in this building, you know, the amount of cooling that's able to offset, because of course, you know, we still need fan coils there. It's not like we're going to be utilizing domestic hot water all the time. There's always going to be fan coils there to help manage the load. But this approach would probably help reduce the amount of active cooling these spaces need by about 20%. Which again is over the course of a year quite substantial, considering this is, you know, a 24/7 load, which is constantly being imposed on the building. And so there you have it. Hopefully, you know, it was a lot of information, a lot of technical information for you to kind of digest, but, you know, I'll leave it here. I'm happy to answer any questions that you might have. This is a wonderful shot, by the way, on the roof where it's absolutely covered in PV, and aside from the couple events that we have of our HRVs kind of poking through at present. But yeah, thank you.